Sumner is at Forest, and I think even though that is not necessarily just focused on your work, I think you're one of the best people to give introductory talks on neuroscience and neurotech, especially on brain-computer interfaces, but pretty much across the board. Sumner has given 2 seminars already, so if you're interested in learning more about his work, perhaps in a longer format than these 6 or 7 minutes that we have here, then please go to our seminars, and you gave 2 fantastic talks. Thank you so much for joining us again, and please take it away.
Thank you, Allison. As she said, my name is Sumner Norman. I'm the co-founder and CEO of a company. We are a focused research organization called Forest Neurotech. And we exist to create the first implantable device that's capable of functional neuroimaging widely throughout the human brain, and also the ability to stimulate function anywhere within the human brain. And this is our vision for whole brain I/O. And the reason that we care about this is because it can enable a platform where therapeutics can actually be developed as easily as software. Quickly, just meet the team. We're up to 14 people now, plus various outsider contractors and so on helping us, and advisors from Verily, OpenAI, Columbia, Caltech. So I just want to recognize that all the work you're seeing today is thanks to these incredible, incredible scientists and engineers. Why do we care about neurotech, and where are we now? I like to share this because we really shouldn't overlook the fact that deep brain stimulators have been around for decades and implanted in almost 200,000 people now. So what you're seeing here is an example of someone who's had a deep brain stimulator implanted to assist with the tremor associated with with their Parkinson's disease. And from the left to the right, when you turn this thing on, it effectively disappears. It's kind of almost magical. Deep brain stimulators have also been used for obsessive compulsive disorder, epilepsy, and a few other disorders are coming online now. And so this can seem really magical, and then the question naturally arises, why is this not just everywhere? Why do we not all have deep brain stimulators? In addition to the fact that they're very invasive, require neurosurgery, they also only treat one part of the symptoms associated with these very complex diseases. So in Parkinson's, as my example, you also have problems with balance, speech, mood, and so on. And so we're treating a very narrow part of that with neurotech today. And of course, in addition to Parkinson's, there are a number of other diseases and disorders that are not well addressed by neurotech yet. Bipolar, anxiety, depression, and so on. It so happens that these are also the most devastating ones that cost the most economically and have the largest treatment-resistant populations, including about 21 million in the US, just with the most severe and treatment-resistant forms of these ones. These all share a few things in common, though, so we can start to think about what the next generation of BCIs have to do if we want to actually address them. The first is that the brain networks are distributed, so they exist widely throughout the brain. They're different between different people, so everyone is different. And they also change over time. And so this tells us a little bit about how we should be thinking about neural interfaces that are different from what we have today. So where are we going in the future with this? If we talk about where we just came from, we need something that is large scale, able to address all of those circuits and systems widely through the brain. It needs to adapt with the person through time, updating to the changes in their disease state or changes to their activities of daily living, or maybe the brain just moved a bit. And of course, we need to maintain that ability to both read and write so we can see the functional effect that the stimulation is having and update it with the person as they go through their life. And as amazing as some of these existing technologies are, we've talked about DBS, many of you will be familiar with Neuralink. These are incredible devices. Neuralink, as amazing as it is, it would take about 6 of those to cover just 1% of the human surface cortex. That's to say nothing of the sulci or deep brain structures that we know are so important to those diseases. So what we're working on is to interface with much larger areas of the brain in an implantable form factor. So we're creating ultrasonic BCIs to do this. So these are the devices that fit entirely within the skull, not in the brain, so they're much less invasive in terms of risk and implantation procedure, but allow you to still interface with those large regions. This is thanks to these really beneficial physics, which Mary Lou introduced us to, where ultrasound penetrates deep tissue very easily. And not only that, but it can be used bidirectionally. So we can send these nice plain big waves out, and then we can record the backscattered echoes to discern where blood flow is perfusing neurons that are more active versus less active, and that tells us something about the detailed function of the brain down to 100 microns in some cases. At the same time, we can then focus those beams with nothing but a change in programming by electronically steering them, we can actually modulate very small sections of tissue in the brain to then nudge them back into the more normative and healthy brain states we'd like to see. This is built on a very long academic history. Well, I say very long, but it feels long to me because I was there, but it's actually relatively new. Functional ultrasound was developed in 2011. We had publications in Neuron, Nature Neuroscience, Science Translational Medicine that you should definitely check out if you want to understand the mechanisms and science associated with this. But this is built on really firm academic underpinnings. So what have we actually done? We've been around a year. This is some of the first time that I'm actually sharing this, so it's kind of exciting. But this is one of our first devices here. I'll get to that in a second. But before I do, I want to just show you what this actually looked like. This is one of the setups in our French sister lab, where this is what any ultrasound researcher would normally use in a lab today. This thing is huge. It's much bigger than me, takes up server racks of equipment, requires a PhD in physics or computer science to actually program the dang thing. But once it works, it is pretty flexible. So what we've been working on, and this is my first time sharing this is what we're calling Forest 1. So I actually have one of these in my pocket. This is, as far as I know, one of the most advanced ultrasound scanners on Earth. It is also very, very small. So if you're interested, if you're an ultrasound researcher, a biologist, a neuroscientist, or a neurosurgeon, ideally, let me know. We should talk, because we're starting to share this with collaborators and researchers. So the system I'm showing you on the left is 1,000 channels. All those publications I showed you earlier were done with just 128. This device has 9,000 channels. It's a 95% cost reduction. We're going from imaging capabilities only to imaging plus neuromod, all built into the same device. And of course, it's a lot smaller, which means you can actually wear it if you don't have a skull. So this is primarily meant for people with severe forms of traumatic brain injury and other diseases where you have already had the skull removed as part of your standard care, or you're using it in an intraoperative setting. We are going to be moving this into fully implantable scenarios in the future, but we're starting with this as our test bed. I'm also excited to share that we have been using this in humans, so I'm showing some example data here. And in this single image, you're seeing both structure in black and white and functional activity in red. So it does work, and I'll be sharing more of that hopefully very soon. It also works in 3D, which we've never seen 3D synchronous images before. So not only is this device very, very small, it is actually the most capable functional imaging device around. We will get into implantable soon, but with that, the slides have frozen. Nope. All right. We'll end there. Thank you so much for listening.
Thank you. Questions, comments? All right, yep, in the back. Feel free to start projecting.
I'm a speech language pathologist interested in speech BCIs, and your device just seems perfect. It seems to address some of the, well, not perfect, but it seems to address some of the issues that are coming up with speech BCIs in terms of being able to do deep penetration, but also be widespread. So I'm wondering, do you have any ambitions to be working with speech pathologies or language difficulties or things like this? If so, how have you been addressing those difficulties?
Yeah, there's a fundamental limitation to what we do, so I want to be very upfront with that, which is that we're measuring hemodynamics. So although we're stable over months, and we've even shown decoders working over years in non-human primates, these hemodynamics are slow, probably too slow for motor representations of speech, which is what most speech BCIs are using. If you are, however, are interested in the semantic representation of speech, or the more abstract, kind of go back one layer in the neural network of our brain, that version is much more feasible. So if you're familiar with the works of Jack Gallen or Alexander Huth, like that style of speech, definitely worth studying with this. If you really care about that temporal precision and super fast accuracy, I think you need to pair ultrasound potentially with genetic modification to start using to actually do single cell or very fast time scale kinetics there.
Thank you so much.
Okay, thank you.